Hi everyone, welcome back to the second video in this three-part series where we discuss how these rate laws come about. Now, the math behind this can get kind of intense, but in this video I want to dumb it down a little bit for maybe those in AP chemistry or just general chemistry who haven't taken a calculus course yet. So what this is going to require us to do is solve this equation to make it, instead of a rate, into a formula. Now, the first order rate law tells us that the rate of the reaction, or I'm going to write this out, the change in the concentration of some reactant A over the change in time is equal, and the depletion of that is equal to K times the concentration of A at that point. So the rate at which this is decreasing is equal to some constant K, which helps us kind of tie everything together, right? It's just like any other constant that you've learned about, times the concentration of A. Now, in calculus, like I said in the last video, please watch the last video, a very small change in concentration over a very, very small change in time, right? I want this idea to make sense. We're now taking the rate from arbitrary units of time, seconds, minutes, hours, and we're shrinking that time interval into basically zero spaces of time, where it's an instantaneous change in concentration over time, instantaneous rate of change, right? Very, 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 very small rate of change, okay? Basically, at some point, what is that trajectory of the rate of change, okay? Or the best fit on a linear scale. This is still equal to Ka, right? Because that rate depends on the concentration of A. Now, we can make, like I alluded to in the last video, this requires calculus to solve, differential equations specifically. To solve this specific differential equation, it's the same thing. It's a separation of variables. That's what you're going to notice for all of these rate laws that I'm going to talk about. Okay? In the last video, we took dt and we shoved it to the other side. We need to get our variables by themselves. Please notice that k does not matter here. K is like a number, 1, 2, 2.5, pi. It's just a number. So we're going to treat it as a number when we do our calculus. So I'm going to just make a step here and say that dA equals negative K concentration of A dt. Okay, so kind of in the last video we separated our variables, but we haven't separated one of the variables, and that's A. When you have a variable that you have a very small change of, or dA or dt, you have to have them on the same side. It's like putting your y's and x's on the same side. We could look at this as dx, and this is x, right? You need to get the x with the dx. Okay, that's just how you're going to be able to solve this. So we're going to divide out this a, and it's going to look a little strange, but you're going to notice 1 over a is equal to, or sorry, I need to put my other bit here, with a very small change in A equals negative K dt. So notice what we did here. We said, okay, the rate of our reaction is equal to this constant K times the first order of A. Makes sense, right? A to the first power, that concentration is how our rate's going to go, right? It's a rate law for a reason, and you'll find this, right? You'll find, okay, this is what we're working with. Now that I have this rate law, I want to make a function where I can plug in a time and get a concentration. That's what you're asking yourself here. So what we did is we used calculus to say, okay, let's make that change in time very, very, very small. Thus, the concentrations change very, very, very small. It's a decreasing rate, so we put a negative equals Ka, or concentration A. We then separated our variables, we multiplied the t and the negative over, and we are now dividing that concentration over. So our variables are on the same side. What we do now is we take an integral. Now, this is going to be like, what the heck are you talking about? Just trust that what I'm saying is right, because I don't want to get into the proof of ln, or the derivative of 1 over x is ln x. Or it really isn't. There's a whole fun video that you can watch about that. But for most of the domain, it's ln a. So we take an integral of both sides with respect to what variable is here. So we're taking the integral of 1 over concentration A with respect to concentration. If it wasn't with respect to concentration, it would be like a variable. We wouldn't even care about it. Same with over here. We don't have any t's. This is a constant. Negative k is a constant. So we're just taking the integral of a constant, which is going to be negative kt. So this side, negative kt. We're going to add a plus c. We'll get to that again in a second. But 1 over a, this is going to be ln of the ln absolute value of a. Right? So please note that this statement is true. When we take the integral of both sides, this is what we get. And if you take in calculus, this should be obvious to you. If not, again, it's just how it is. Now I want you to notice that what is C really? Well, for practical purposes, I don't want to solve for C right now. We're going to solve for it maybe a little later, and we'll see why that is. So to undo this ln, we take e to both sides. And you're like, well, why would you do that? Well, we want to get concentration by itself. When you raise ln, or if you raise e to the ln, they cancel out because they're inverse functions. It's like taking a sine function and then using sine to the negative 1 on it. Same kind of thing. So you get the concentration of A absolute. Although you couldn't really have a negative concentration. So for all practical purposes, we'll just get rid of the absolute value brackets because it's not going to matter. So it's going to equal E to, and we'll say C minus KT. Here. So I kind of just swapped these two to be C minus KT, and then we raise it to the E. There's a cool little idea that you can use where you can separate these by saying, okay, well, instead of E to the C minus KT, there's a rule that says, okay, if you have E to the M plus N, you can write this as E to the M times E to the N. It's the same thing we're going to use here. We're basically just going to say that E to the C times E to the negative KT. Here I want to solve for our initial concentration. If we plug in 0 for time, we can cancel this out, make it 1. E to the C is going to equal A. So, and what we're going to do is, because I want to make one more simplification before I move on to this, even before we talk about this, because it's going to make it a little easier, I'm now realizing. If I define E to the C as another constant, it's going to help us here. So this is going to be C sub 2. So C2. Because E to the C is still a constant, and if we solve for it, it's going to give us the same thing as E to the C. We're just now saying it in a more generalized form as C2. So when we plug in 0 now, E to the negative KT becomes 0, so this would cancel. And then we're just left with our constant is equal to the initial concentration. So if we say A is equal to our initial concentration, so A, or the concentration of A initial, E to the negative KT. And what you'll notice is this is actually the second order integrated rate law. We found it using calculus, specifically differential equations, but we found it. And this is how this integrated rate law comes to be, is through calculus, right? So if you're looking at this and you just want an explanation, maybe you don't know why, maybe you do, through the calculus, maybe you know the calculus, maybe you don't. It's just a way so if you're curious, you can understand. And I tried to explain it the best I could. The math gets a little strange because, again, you need to know integrals, derivatives, all this stuff. But besides that, that's how it comes about. And yeah, that's going to be it for this one. That's the first order integrated rate law. And in the last one, we're going to look at the second order integrated rate law. So I hope to see you in my next video. Bye-bye.